Welcome everyone. My name is Thomas and today we are talking about Proposition 15 of Gottfried Wilhelm Leibniz's work on the arithmetic quadrature of the circle, ellipse and hyperbola. And in Proposition 15, Leibniz is describing a theorem which was originally discovered by Michelangelo Ricci, who was a Roman Catholic cardinal in the early 17th century. And the very theorem which Ricci discovered, he described in a little treatise which he himself called Excitatio Geometrica de Minima e Maxima. And there he just basically proved what Leibniz was actually describing here in Proposition 15. And Leibniz was very explicit in stating that he did not need to prove this theorem again because it was already proven by Michelangelo Ricci. And the theorem is about the following things, which we are going to describe now. First of all, let's start with the example of a simple parabola. So we have the analytic expression, as we went on to explain in the definitions part of Proposition 14. We make up of a y entity and a v entity, and we always make sure that the parameter p is compensating for the missing dimension on one side of the expression. So the sum of the exponents of this side of the equation is always equal to the exponents or sum of exponents of this side of the equation. And by this condition we can draw out the relationships as Ricci has done. Leibniz also uses often the word dignities, and this word I think I used also a couple of times before already without explaining what it means. When you call back into your mind the very expression or analytical expression which we were just looking at in form of these equations, we had a side of the equation where we had a y and the other side where we had a v, and both of these numbers could have different exponents. So the y, including its exponent, for instance, would be representing a dignity, whereas the v part, also with the various possible exponents, would also define a dignity. So when we take dignities here, we always talk about the y and the v as abscissas and ordinates and their respective powers. So this is all that's to be said about the term dignities. Back to our little construction. Okay, so we have this pi handle. According to the definitions part in Proposition 14, we use it as the parameter. So the distance a pi is basically constituting the quantity p, which we use as a parameter. And as I change the parameter, of course, I will either stretch or skew the parabola accordingly. And now we go into the details of what Ricci actually discovered. So when you place a point on a location on the parabola curve, and you draw a tangent from this point upwards such that it at some stage intersects the extended axis, it will intersect this axis then in a point that which we call theta. And Ricci discovered that no matter where you place the point on the parabola, that the distance between theta and b and a, b, so basically the proportion between the intersection point theta to the abscissa and the abscissa itself will always stay the same. And he found that this proportion actually exactly matches the proportion of the exponents of the dignities. So we have omega as the exponent of the y dignity, the dignity of the ordinate, and we have the e as the exponent of the y dignity, which is the dignity of the abscissa. So, and Ricci found, and he also proved it in his treatise, that the proportion of the distance theta b divided by AB, being the abscissa, is equal to the proportion of the v dignity, or the exponent of the v dignity, divided by the exponent of the y dignity. And in case of the parabola, this is of course 2, because the ordinate dignity has a exponent of 2, and the abscissa dignity has an exponent of 1. Alright, and that's basically the whole principle of what Ricci discovered. And he also discovered that this is not only true for the parabola, but basically for all the paraboloids. And this is we're gonna now look at for the cubic parabola, for instance. Let's say we have a cubic parabola like this one now. So it is described by the exact analytical calculus of the parameter square times the abscissa equals the cube of the ordinate. And when we draw a tangent now from our point C, O, and we look at the very distances which we did before, then it should be that theta b divided by AB as the abscissa should still be equal to the exponent of the v dignity, being 3 in this case, divided by the exponent of the y dignity, being 1 in this case. So this is giving us a ratio of 3. And we can basically only visually verify this, that this is actually true. So theta b is indeed about as 3 times as long as the distance of the abscissa AB. So this was proven by Ricci, and Leibniz was using it to his terms in the quadrature. And also for the example of the semi-cubic parabola, so if we, for instance, make the exponent of the y dignity higher than 1, and this we can do by semi-cubic parabola. The curve looks like this. It's a little flatter because we now double the cubic parabola, which makes the curve a little flatter in general. So we have the parameter p. This time its exponent is 1, because we need to make sure that the sum of the exponents of both sides of the analytical expression are equal. So we have exponent 1 for the p, then exponent 2 for the y dignity, and the exponent 3 for the v dignity. So 3 as the sum of the exponents equals 3 as the exponent of the term on the other side of the equation. And it indeed still holds true. So theta b being the distance between the intersection point of the tangent with the axis and the very abscissa end, b0, is this divided by the abscissa itself should constitute a ratio which is equal to the abscissa, or the exponent of the v dignity, being omega, so in this case 3, and the exponent of the y dignity, namely e, being in this case 2, and thus giving us a proportion of 3 halves. And we again visually verify this, and indeed the distance theta b seems to be about 3.5 times longer than the distance b as the abscissa itself, and this is actually true indeed. Okay, now let's look at the hyperbola. So for the hyperbola we have slightly different arrangement of the analytical expression. So we have the v and the y dignity now combined into one term of the equation, whereas the parameter is standing by itself now on the other side of the equation. We again make sure that the sum of the exponents of all dignities is equal on both sides of the equation. We do that by means of the parameter. And indeed, if we look now to the distances and their proportions, we already see, or again see, that the tangent of the point intersects the axis in some point theta. This point theta is now, due to the sort of inverse nature of the hyperbola as compared to the parabola, is some point lower than the origin point of the axis, or even as well as the point of the abscissa end itself. So let's see if the proportion which Ricci drew out still holds. So let's say theta b is this one, divided by AB is now supposed to be equal to the proportion still of the v dignity being omega. So this is 1 divided by e as the exponent of the y dignity, also 1, and this is giving us a proportion of 1. And if you visually verify, you see that this is actually true, that the proportion of theta b as this distance divided by AB as this distance is always the same, and in case of the hyperbola is always 1, no matter where you place the point on the curve of the hyperbola and no matter how you arrange the parameter. This ratio always stays the same. It's an invariant of the hyperbola, or of any curve which is of a paraboloid or a hyperboloid nature. This is what Ricci found out, and Leibniz was using this proportion or this relationship between the proportions of these axis distances determined by the tangent and the ordinate and the exponents of the dignities of the analytical expression. He uses this relationship extensively, and it actually later on enabled him to sort of define the rules which led to the very capability now of students or whoever applies the calculus to, for example, create the first derivative of analytical functions, as they are called today. Because you can imagine that knowing the analytic expressions, you also know always the exponents of their dignities, and because of this very theorem of Ricci, you can use this always to calculate the slope of the tangents. And the continued representation of the slope of the tangents, that's actually nothing else than what the first derivative represents. And by the means of this relationship, the rules of how to create the first derivative of an analytic expression was established, as you may know from school. So this was the very basis on how which this was developed. And also in terms of the integration part of the calculus, this very theorem here and some further continued elaborations on it also led to the fact that or the discovery that the areas of certain curves and their complementary areas also stay in a very distinct relationship to each other, or very distinct proportions, which also have solely to do with the proportion of the v and the y dignity in the analytic expression. And but this we're gonna have a look at in the upcoming propositions of 16 through 18, where we are dealing with these things. So if you are interested in a more detailed view of these things, or you want to take your time elaborating or exploring things on your own speed, you may go to the very propositions part 15 of this little website animation here, and yeah, you may take your own time in thinking about these things. And it is indeed very rewarding, I can tell you. All right, so this is everything for now on Proposition 15, and I hope you stay tuned and keep watching. Thank you very much, and bye for now.